Good morning, FOR 345. Soils isn't a spectator sport, so I thought I'd come and broadcast this live from the Super Bowl Stadium. Welcome to another exciting day for FOR 345. And what I'd like to do is remind us where we've been. So last time we talked about our points of reference for available water. We talked about the soil moisture characteristic and actually spent some time calculating it and going through the graph. We then compared mass versus volume, thinking about soil water. And we ended up talking about movement. And we may have gotten a little bit to measurement. So kind of review a little bit of movement, and then we'll continue on with our story as we head towards soil aeration. So water flows in response to a gradient. This is and the gradient is always the same. And so I've listed it on this line. So we're looking at water flowing going from the right to the left. And we see free energy going from positive to negative free energy. So we can think about this scale in a number of ways. And no matter how we think about it, it's this gradient, no matter what we call it. So first, we can think about free energy. So if we think about this gradient number line in terms of free energy, we can look at water flowing from higher free energy to lower free energy, always from right to left. Okay? And we can think about that as potential, and we define potential as the difference in free energy between water at a point in the soil solution and some point in the soil. And water flows always in response to a gradient of higher potential to lower potential. And we can illustrate that with numbers, positive numbers for high potential, and more negative numbers for low potential. We can also think about that in terms of the size of the pores, and water flows from large to small pores. And as pore size gets smaller and smaller, water will be drawing to those pores more and more. We can also think about that as films around soil particles, along with pore size. And we can think about water flowing from thick films to thin films. Okay. And then we can think about that from the other side of soil moisture tension. And everything is the same, but now soil moisture tension, we talked about considering tension as the viewpoint from the soil. We're now looking at positive numbers and more positive numbers. So no matter how you cut this gradient, whether you express it as free energy, whether you express it as potential, whether you express it as pore sizes or the film size or tension, water always flows in this gradient. So tension versus potential, maybe it's useful to kind of review that idea a little bit. So the same magnitude and the differences in direction or perspective. Okay? And remember that potential, the perspective of potential, the difference from a pool of pure water, which we assign as 0, and we have this negative number because anything less than pure water held by the soil will have lower potential. Okay? So viewing that from the soil, it's negative. It's a negative potential where it's going to take, we actually lose, it takes more energy to hold that in the soil. But if we think about that from the soil's perspective and turn that around, instead of looking at it the perspective of pure water, we can think about the soil doing the work, the soil exerting a suction. And so from this perspective, we think about a positive number. The soil is exerting this positive number, this positive holding power. And so it's the same magnitude, but now we have positive numbers instead of negative numbers. And that's the big difference. It's all about perspective, where the reference point is. Okay. So let's think about flow, and let's think about saturated versus unsaturated flow. So we think about saturated flow, we use Darcy's law. And Darcy's law is stated here in the slide. QT is equal to A area times Ksat over the change, the delta psi, the delta potential over length. And what's that mean? So we can think about this as a container and think about what are the common values and what are the fixed values and what are the variables in this container. So first, let's think about flow. And we express it as quantity of water per unit time. And so Q over T is the way we express flow. And then we're looking at saturated conditions. That is, all the pores are filled with water. Okay? And so let's break this down. So we have A, area, all right? And that's kind of a function of the size of the container. Okay? We have the height, okay? And the psi, the difference in height, times the gravitational potential. And that's kind of a function of the container. So those two pretty much are a function of the container. Okay? And so let's express this. So we have quantity of water per unit time, and we express it oftentimes in centimeters per hour, centimeters per second. But those two units, it might be gallons per hour, gallons per minute, but those are the units for saturated flow. Okay? So let's isolate Ksat. And so if we take the container and get that out of the picture, we can isolate that piece called Ksat. So we rearrange that equation, and we ended up with Ksat is equal to Q over AT times L over delta psi. And this is just an algebraic rearrangement. So what have we done? We've taken everything that has to do with the size of the container, isolated on one side, and now we have a variable Ksat. Okay, so this Ksat kind of reflects the rate of water movement for any given area and any given height. Okay? And so Ksat is the saturated hydraulic conductivity. The saturated hydraulic conductivity. It's a number that expresses the rate of water movement for a given size container, a given area, a given length. Okay? And so what does it represent? So think about what that represents. That's a function of the pore size, the pore shape, and the conductivity. So that number, that single number, is this integrated expression that reflects size, shape, and conductivity, and that controls the rate of water movement. And so that Ksat is a pretty useful number because among all soils, it's a kind of, we can use a constant container size, a constant area, and a constant depth, and then express the rate of movement, which reflects the size, shape, and conductivity of the soil pores. So that's a pretty useful variable, a pretty useful number, a very useful concept. You can go through any of the soils of the US and the NRCS, and they're posted or express numbers that express Ksat for almost any soil series. And that's one of the ways we use to model soils and movement as we think about using the information from the soil survey, is to have an idea of the rate of saturated conductivity. That has all kinds of uses, right? When you're thinking about drainage, when you're thinking about septic tanks. So that Ksat is a very important number, that expresses the integrated movement of water. It's very important in soil physics and very important in practical applications. So let's think about Ksat. What are the physical properties that would give us a greater Ksat, a higher rate of saturated flow? What would we think? So we would think about the texture and the structure. So a sandy texture with generally large particles and macropores, a high proportion of macropores, that would give us a high Ksat. And stable granular structure. So remember granules, those beautiful little pieces that have large pores between them and hold water. So that combination, or those two variables, would lead to a relatively high Ksat, a high rate of saturated flow. Saturated flow takes place through the macropores. Think about that for irrigation and texture. And so here's a picture from the text, figure 520, page 208. And it contrasts the sandy loam versus a clay loam for irrigation. And we've plotted depth on the y-axis and distance from the center of a furrow, the irrigation furrow where the water's coming in, is illustrated along the x-axis. So the sandy loam, we look at this and there's a relatively narrow rate of spread of that water, and it moves down rather quickly. So in 15 minutes, it gets down to 30 centimeters, and then in 40 minutes, that water will penetrate to 90 centimeters. In an hour, the water will penetrate to 120 centimeters, and in 24 hours, you're down to almost 2 meters. Okay? And it's a very narrow spread. So mostly the movement is downward. There's very little lateral movement. Now we contrast that to a clay loam, fewer macropores, more micropores, and we look at the difference, and the rate of saturated flow is much slower. So instead of taking 15 minutes to get down past 30 centimeters, it takes about 4 hours. Okay? And then 24 hours to get down to 60 centimeters. On the sandy loam, then 24 hours, we're down to 2 meters. And concurrent with that reduction in downward movement is a lateral spread. So this lateral spread is much wider. So the saturated flow rate is impeded, and the lateral flow rate across is enhanced. And so that's pretty important in terms of irrigation, thinking about where you locate your irrigation furrows and so forth. So an interesting application, and so we tie that back to texture. Texture, one of the important physical properties. We made some generalizations about water movement. Now we can tie that directly to Ksat. We're describing water movement, saturated flow, using this number Ksat. And here we see the impacts of texture. Pretty useful. 15 minutes versus 4 hours. Astounding. So let's think some more about saturated flow, and let's use the term preferential flow. Okay. Preferential flow is this term that also describes saturated flow. And so when we define this, we can specifically attach some ideas with it. It's non-uniform water and solute movement through the soil. And so largely we're talking about macropores. So here we have a pretty rapid movement of water through macropores taking place. This water also carries solutes, so the whole soil doesn't wet at once, right? The water movement isn't automatically through the whole soil. It goes through channels first, and you get this saturated flow to large pores. So we refer to that as preferential flow. And it has some implications because when water flows, it carries with it solutes. And this is how we move a lot of fertilizer, a lot of nutrients, a lot of herbicides, and so forth. If they're soluble, they move through preferential flow, through the macropores. Okay. So free water, saturation, you're at zero potential, moves through megapores, preferential flow. So let's contrast this to the unsaturated conditions. Okay. It's about 100 times faster, 100 times more than matrix flow. Okay. So the rates are very different. And down and around live roots, these are macropore, large preferential flow. This is part of the flow through the soil. And so what can happen is all this water moves to the soil very quickly, and a lot of the fine textures are not wetted. And so this idea of preferential flow, preferential movement, due to this rapid flow through macropores, and most of that water going through, and some of it, much of it, not retained. So do you see the problem? The problem is, let's say I also have fertilized this field, or I've applied some kind of nutrient, I've applied maybe some kind of herbicide, some kind of pesticide, and so when water moves, and soluble things move with it. And so this is how materials move. They move the saturated flow, preferential flow. And it's a pretty important consideration, so you don't want to fertilize and then irrigate at the same time. Let's look at the rates. And so we made some distinctions about soil texture and the rates of saturated flow. Here's some quantified numbers from table 5.3. Okay? And so I have a substrate with increasingly fine textures and the Ksat in centimeters per hour. So we look at beach sand, has a very rapid saturated flow. In an hour, you can 36 centimeters of flow through. If for something of moderate permeability, maybe a loam soil, a sandy loam, it's almost a magnitude of order difference. And then we go to a fine texture, and yet another order of magnitude. And then if we go to a compact clay, we take some clays and actually make an effort to compact and increase the density. It's very, very small. So this is one of the reasons why we use compact clays as liners in where we don't want water to move. Things like waste beds and things where we have disposal sites, we'll use a compact clay, and this essentially eliminates or greatly reduces water movement. It contains the water. It's kind of almost like a fake plastic, a fake layer. Not a fake layer, but a layer that's impermeable. And so 3.6 times 10 to the minus fifth, that's virtually no water movement. And so that's how we keep water from going into systems from leach fields and so forth. So that's unsaturated flow, and so it's coming through the micropores. So what drives it? So think about the gradient for saturated flow is gravity, okay, the force. For unsaturated flow, the gradient is driven by matrix potential. And remember, we talked about the matrix potential, the capacity of the soil to attract water, the soil solids, and reduce the free energy. And we define that potential as psi sub m. And we said it was negative, it reduced the free energy. So a gradient in matrix potential results in a gradient and takes care of unsaturated flow. And it's always from higher potential to lower potential. The rates order of magnitude lower than saturated flow, 10 to the minus 3, 1,000th the rate. So now we're talking about a very relatively small movement of water that's not unimportant, but in terms of the amount of water that moves by saturated flow, it's a very, very small fraction. So consider how we get a greater gradient in matrix potential. And we said that clays are very small pores. They hold water. They have a lot of micropores. So as you increase the clay content, finer and finer texture, you get a greater gradient. There's a greater potential for a difference in unsaturated flow, a much larger gradient. So if you have all sand particles, there's very little matrix force. You have a lot of clay particles, there's a lot more clays holding on to water, and so that sets you up with the possibility for a wider gradient. And so unsaturated flow is greater in fine textured soils. That would be the supposition. That would follow from this idea of water movement in response to a gradient. Now let's take a look at a graph that expresses that. So this is a graph from page 213 in the text. It plots hydraulic conductivity on the left. You'll see the familiar QT, centimeters per day. It's on a log scale. And on the x-axis, you'll see the matrix potential. And you're familiar with potential. We've talked about that. We did that in the graph last week. And here it's on a log scale. And so we're looking at bars, the first line, 0.001, minus 0.01, minus 0.1, up to minus 100, and then convert it to kilopascals. So remember, how do we convert bars to kilopascals? It's a factor of 100. So 0.001 minus bars is minus 0.1 and so forth. And minus 0.1 is bars is minus 10 kilopascals. So just remember to review that. I may ask you to be familiar with that on an exam. And now we'll look at the pattern. So this pattern for hydraulic conductivity shows a sandy loam being greater than a clay soil. So a coarse textured soil has a greater hydraulic conductivity than a clay soil. Okay? And let's look at the second piece of that. It flips. It flips. So as we get down into the drier portions, the lower potentials, the clay soil has a greater rate of hydraulic conductivity than the sandy loam. So we have fine versus coarse, and that flips. This is pretty interesting, right? We have a change in hydraulic conductivity or a change in the rate of flow. And let's look, where does that occur? Where does that shift occur? What's the point in potential where that changes? Okay? And it's right about there. Okay? So if I look down and try to understand what's special about that inflection point, or that where those two things change. What's special about it? You should recognize that that is about the potential for field capacity. And field capacity is the point, and remember we said that was the point after 2 or 3 days after a soaking rain, when all the macropores had emptied and the micropores had filled. We called that field capacity, and we gave that a potential somewhere between 0.1 and 0.3 bars minus, or minus 10 to minus 33 kilopascals. And that's a pretty important difference. Okay? And that's field capacity. So this graph says that the hydraulic conductivity effective texture changes from saturated to unsaturated flow. Pretty amazing graph. So this shows us saturated flow. All the macropores are filled with water. And on the left-hand side, and the sandy loam, is much higher rate of hydraulic conductivity. We passed field capacity, and now all the micropores are filled with water, and that's where you see this flip. Now the clay soil has a greater hydraulic conductivity than the sandy loam. Okay, so that's a very nice, so this graph you want to keep in your head, because this is a very important link of soil texture and flow rates of saturated and unsaturated. So this is useful. So let's think about saturated flow. Now we've identified it, we've defined it, we've talked about how it differentiates both in pore sizes and how it's differentiated in quantity compared to unsaturated flow. And let's look at a practical example. So here's a pretty interesting study that was done in the mid-70s by the Forest Service, and they had a very large oak stand. And they actually did some artificial rain, applied artificial rain to some very large plots in this beautiful oak stand. So it was a mature oak hickory stand. There's a sandy loam site and a silt loam site, so a relatively coarse and relatively fine texture. And some of the measurements they made were Ksat. So one of the ways to measure Ksat, the rate of saturated flow, is to use a core. So take a core, bring it into the lab, run water through it, measure how long it takes for that water to move through, and then compute a Ksat. Another way to do it is do it in the field. So they also looked at these big outflow pits, very large plots. They had 10 feet across and 4 foot deep down the side of this slope, and measured what came out the bottom as they applied artificial rain to the top. And after they did that, they kind of took this apart. They go back to this big 10 by 4 foot piece, and they took it apart piece by piece and kind of graphed it, what they saw at the area. So they looked at the morphology. And this was a pretty interesting study. It's a large study, as only the Forest Service can do and invest this kind of money. And it's pretty unique. Now we'll look at some of their findings, which are outstanding. So here's the results from the lab. So I'm going to show you a graph that shows the Ksat from the 6-inch cores. And here are the results. What happens is that the Ksat decreases with depth. So deeper and deeper in the profile, the Ksat gets lower and lower, or less and less. So consider why. What happens at the top? At the top you have all this organism activity, freezing and thawing, wetting and drying, all these animals and roots. Those are concentrated very heavily at the top. And as you go deeper in the soil, those things decrease. And so the macropores decrease. Density increases. And so with that decrease comes a decrease in Ksat, because Ksat occurs through the macropores. Okay? And also over time. So if you take the same core and you measure repeatedly and do this test over time, the Ksat will get smaller. And what happens is that as you keep taking the same core and pouring water through it, is that there releases some soil and there's some plugging. So the Ksat over time will be reduced because of some plugging. Here's an illustration of that. Here's the graph. It shows hydraulic conductivity in the familiar units, centimeters per hour on the left on the x-axis, going from 0 to 160, in the two sites, in our site A and site B. And it shows the change over time and depth. So here we have the 0 to 6 inch depth for the two sites, the 6 to 12, and so forth. And so the pattern is pretty interesting, that the Ksat is very high and it decreases with time. Now here's a look at that, a visual. Kind of interesting to think about what that looks like. So they go back and they take apart that soil pit and kind of graph the face of it. So here's one of the graphs of faces, and what you see kind of is a very fine explanation for the results. So at the top soil, at the top layers in the A horizon, you have a tremendous volume. About 30% of that soil are these huge, called megapores. These are pores that are large channels filled with organic matter, dead root channels, and this is in addition to just the macropores. These are large pores that are created by organisms. So about 30% of the soil. So you can see a rather phenomenal range, and so these are just loaded. 30% of that volume of that soil is loaded with these large pores. So it has really high capacity for infiltration and percolation of water. And as you go deeper and deeper, those pores dissipate. They become much less common, and Ksat goes down with depth. So here's some numbers. Here are some numbers for that with the horizon and the surface area of these so-called biotic macropores or megapores. And if you go for the horizon, they have an A, E, a BW, and so forth. We go down in depths, or 0 to 1 centimeters. So you're familiar with this expression of how we measure depth. And think about soil profiles, and we have 0 to 1, 1 to 6, and 6 to 9. So that should be perfectly familiar to you. And then the proportion, the percent of biotic macropores, and a precipitous decrease with depth. So this is the reason why forest soils are so accepting of water. You can throw a hurricane at a forest soil, an undisturbed forest soil, and you will not get overland flow. The combination of these large biotic macropores and the stability of that surface with the leaf litter and the canopy, preventing any kind of disruption, that provides a tremendous capacity to move water through the system, even at hurricane levels. However, you can destroy this. So if you want to reduce the capacity to transmit water, you could rut and compact. In that case, that would make these biotic macropores significantly reduced. And then you would start to see overland erosion. So this is one of the reasons why forest soils are measures of our natural rates of erosion. This large capacity to move water through intact forests is tremendous. So we can kind of capture that and summarize it. This we showed you a lot of data from a very interesting study, a very expensive study. And again, only the Forest Service has the capacity to do these large, long-term studies that take a lot of manpower and a lot of forest capital to boot. So saturated flow, if we could summarize what we just talked about, it occurs in forest soils through these megapores, these biopores. They're root channels. Animals and insect burrows, oftentimes they're filled with organic matter, but that's a very high volume, a very high proportion of the surface soils for forest soils. Most of the root channels are found in the upper 2.5 feet, and so that's where all the organism activity. So Ksat decreases with depth, all those large pores decrease with depth, everything that is responsible for moving water and letting gravity do its work decreases with depth. And say, as we get into finer textured soil, there's a very interesting impact. Finer textured soils, they tend to have their structure, they hold together a little better. So root channels will tend to dissipate less. So as roots decompose in fine textured soils, those channels tend to stay coherent. They tend to stay in sight. And so when you get these finer textured soils, tend to have a larger proportion of old decay root channels, which is maybe counterintuitive. We think about sands. But sands and the structural capabilities of sands are much less than fine texture. So throw in a little clay and a little organic matter, you have some very nice structure, and then these megapores will stick around longer. Okay? And so we're thinking again, we're talking about water movement. It's free water moving through the megapores. And we're remembering this is preferential flow, and it's about 100 to 1,000 times matrix flow. Okay? So big difference in the amount of water. And we've also got roots. So if you've ever cut through a soil pit and looked at one in the rain, and a few of you have even this year, not too many days of that, fortunately, but a few of you have done that as we've gotten poured upon at a couple of our Heiberg. I think maybe only one. If you stood there long enough, you'd see the water coming right out of those root channels. And that's another way that the saturated flow occurs through forest soils. And so because of that, much of the fine texture around that could be not even wetted. And so this preferential flow moves down along these root channels and through these megapores and may not even wet the finer textured pieces. So I want to just kind of wrap that up with some work done by a study in quite a few years ago now in SSSAJ. And the reason I use this one, so Jeff McDonald, who was a former professor here, this is one of his students, and they did this work in Japan. He did a lot of work in Japan. And so they had this beautiful study along a watershed, quite well instrumented. And they used a dye to track where the water was. And so it's pretty interesting to see water, and so these white dyes, you can see water moving through these old decay root channels, okay? And you can see it moving through these large biotic macropores. So tremendous water movement. This is kind of illustrating that with a dye. And then the interface between the B horizon and bedrock, okay? So at that interface, there's a lot of water movement. So this is a pretty outstanding paper that provides a very good visual of these ideas of water moving through these forest soil systems, and it's just a visual of how large those pores are. And you put that together in a very nice diagram, and here's a pretty good summary of it. You've got these highly permeable soils. Okay? You have water moving downward, moving preferentially in preferential flow. There's a lot of movement across the bedrock, water moving down through large root channels, and essentially no overland flow in this forest soil system. Okay? And then it's also illustrating the movement through live roots. So you kind of remember this picture, and it's a very good illustration of the systematic and sometimes random location of these biotic macropores, both in root channels, decaying root channels across the bedrock, and then through the soil. So a lot of this soil may not be wetted, but all this flow, the large amount of this flow moving through these large biotic macropores and along root channels. So we've looked at saturated flow, we've looked at unsaturated flow, and now we have the last piece is vapor. So then vapor, now we're talking about a very small amount in terms of quantity, but still a significant movement for some ecological processes. So this is an illustration, and just like water, vapor movement occurs in response to a gradient. And it's two parts of the gradient. There's a vapor pressure gradient and a temperature gradient. So vapor, in terms of temperature, moves from warm to cool. And that's illustrated here on the left-hand side. Now, in terms of vapor pressure, it's the opposite. It moves from moist to dry. So here we have, in a moist, cool evening, from a dry, warm soil, the vapor pressure moving from the soil would be, they'd cancel each other out. This would be very slow, very low. Now, we can imagine a case where those gradients work together, and so moist, warm soil going into a dry, cool atmosphere, this would be a very high vapor movement. Okay? So these gradients can work together, moisture and temperature, vapor pressure and temperature, or they can work together, they can work apart. And that is vapor movement. So a question, we can now ask a question with all this in mind. And so we think about applying this in terms of a practical question, and we think about management of farms and forests, and then we think about eutrophication and water quality. And so we might link these, and so we might ask, how do nutrients and pesticides move through the soil so rapidly? Is it saturated flow, or is it unsaturated flow? What would you think, or what would you conclude based on what we've talked about thus far? So you'd have to conclude saturated flow or preferential flow. And again, we think about eutrophication and movement, and when we have to worry about water movement, and we even think about the BMPs, is shortly after logging jobs and shortly after operations in farm, any of these operations, when we have an impact on soil and start to crush structure, reduce structure, and we start to affect preferential flow. So we kind of keep in mind that most of these solutes are moving through the system under preferential flow and saturated flow. Pretty cool. And then we can think about management. And so the other side to this is to worry about drainage. And how do we increase the aerated zone and reduce the impact of water on the surface where we're looking at roots and other things and basements. And then we'd be talking about soil drainage. Now in a couple of weeks, we'll get to see a really extensive system of drainage when we go look at organic soils that produce these amazing aerated zone, these beautiful organic soils. And so we have to look forward to, in a week or 2 weeks, our last field trip of the season when we go to Palermo and look at this and see this kind of in the flesh, as it were. But now we'll kind of talk about it and set that up. So let's talk about subsurface drainage. So here's an illustration from the text showing about the effect of drainage ditches. And so if we install ditches, we can lower the water table. And this illustrates, here's the water table before drainage. We install ditches, and then the water table drops. And what happens is, water moves from high to low potential. And so what we do with these ditches is we create zones of relatively high potential so that water will move toward them. Okay? And this is the essential value of drainage ditches. And you space them, so you'll note that the greatest reduction in water table or increase in aerated zone occurs at the bottom of the ditch. And as you get away from that ditch, and the water flows to that point, and so it ends up getting these so-called hills, right, or higher points. So if, in order to control this water table, if we're managing a root zone, the spacing of the ditches is very important. And and the spacing of ditches depends on texture. And so we'll talk a little bit more about this in organic soils. It depends on the rates of saturated flow, and this will have some pretty interesting impacts. But here, this illustrates that the water is moving from high to low potential. Okay? And here, the water potential, if you dig this, is greater than zero. Okay? And we're moving from less than zero, so we're moving that water from a high to low potential, and that's the ditch, and a very nice illustration of the impact. So the goal for this is to increase the aerated zone and allow these plant roots a little oxygen. We can do the same thing with drainage tiles. So drainage tiles refer to pipes, buried pipes, which allow transfer of the water out. Now this is kind of interesting to do, and here these are perforated. They're perforated on the bottom. We try not to perforate them on the top because then we try to keep the soil out of them. So this is one way to keep them from filling up with soil. So these are installed, they're buried, and they have a gradient. So we're looking at the slide, I have this left arrow, so the water flows from high to low potential. In order for water to flow, there has to be a gradient in this pipe. This pipe has to be angled down gradient. Okay? And so eventually we move that water, so there's a third dimension here we're not really seeing or thinking about. But water moves from high to low potential, okay? And so it moves towards these drainage tiles, and it's the same effect as a ditch, but these are buried. And you have the same kind of thing. The drainage tile spacing determines the shape of the water reduction in depth between the pipes, and we get the same thing. So whether you're using a ditch or whether you're using a drainage tile, you have this same effect. Now let's look at saturated flow with some dyes, and this will illustrate the same thing. So this is a setup. This is dated. This is an old slide, and this was the way it was commonly displayed. But this essentially is dyed water and flowing through a sand, and you can see the water movement, and you can see what happens when we insert a little bit of a drainage tile. Okay, so. So you can see this rate of saturated flow, it goes downward, hits an impermeable layer, and goes across. And that's just a beautiful way to visualize saturated flow. Okay. Now let's think about one more. So we've looked at applications for agriculture. Let's think about applications for you, the homeowner. Or you will be a homeowner. Everything goes well in the next 10 or 15 years. Here are two conditions, and we have a water table, a high water table, and a basement. And this is a common problem that hopefully, and so here we need a sump pump because we have a high water table. The basement wall is a little bit permeable, and basement water will flow through and into the basement and will fill up your basement, and unless you have a pool there, you will not be a happy person, or you'll get rid of your basement. This is the left-hand side, shows some difficulties. Here we have water that's going right toward the foundation. This gradient is sloped, and so water is going down and sloping in. So this is what we want to kind of avoid. So how can we fix this when we have a situation like this? So we can use some drainage system. And typically we'll use a drainage tile or a French drain. Okay, so we want to get rid of that. And here we'll grade. So the solution is to grade that first going away from the house foundation, and secondly to install a drainage tile, perforated drain type. So this flows from high potential to low potential, and essentially we have this amazing way to collect water. And now, instead of building up and going to your basement, water is brought to this drainage ditch and tile, and now it's graded away and moved away. And so we have water moving through gravel. So you paste your sand and a little bit of gravel, so you have a lot of large macropores. Water is attracted here. And this is how to prevent the system from having a wet basement. This is called a French drain. So we've looked at saturated flow, we've looked at drainage as a way to manage water tables, and we'll see that again when we looked at organic soils. And now we'll ask the question about roots. How do roots get water? Do roots seek out water? And it's more or less the same story. Roots don't have an ability to seek water, but they create a gradient, and water flows from high to low potential. And so that's illustrated nicely here. So here's a root cross-section in a moist soil. Okay? And as the soil dries out, the root absorbs water, and the soil dries out, and water starts to flow from the gradient. So as this is being a low potential here, there's higher potential, and water flows along these large diameter, let's say thick films to thin films, and the direction of water is to here where water is being absorbed. So this is a higher potential and a lower potential. And this happens until you get to about minus 15 atmospheres of potential, at which point this root can no longer exert enough force, and the system kind of breaks down and the soil dries out. So it's a gradient potential, high to low potential, water flowing. And it's, again, now we're dealing, is this saturated or is this unsaturated flow? Okay. This is unsaturated, right? This is the importance of unsaturated flow. Although it's 1,000 or 100 times less than matrix flow, it's extremely important on the distance of roots. And so roots obtain their water through unsaturated flow. Remember, available water is the difference between field capacity and wilting point. So we don't consider saturation and gravitational water when we calculate available water. Roots grow into moist soil and they persist. If the soil dries out, then they don't persist. Okay? So this is a very important process. And we can think about that as unsaturated flow. Another way to describe that is capillary flow or capillary movement. Okay, so now we have water to the roots. We've gotten the water there. Now we can talk about the devices. How do we measure soil water? Okay? And so there's many ways to do it. Some are more expensive than others. There's different technology. And the things to consider are the application. Are you dealing with very wet or very dry systems? The expense, what do you have in your budget to do this? And do you need destructive versus non-destructive? So just like bulk density, we have destructive and non-destructive methods. The destructive ones, you bring the soil out and measure it, it's gone. You can't go back to that same spot. Non-destructive, you go back to that same spot. And so these are the same issues in measuring bulk density, kind of, as measuring soil moisture. So let's talk about neutron scattering. Neutron scattering. We don't use this for organic soils. And I'll ask, so how does neutron scattering work? So the idea behind neutrons is you have a source of neutrons. You send that out, and it comes back to a scale, and that measures the rate of return. And what happens is that hydrogen slows down neutrons, and the amount of hydrogen is correlated with the amount of organic matter. That's a problem for organic soils, but when you have less organic soils, that's a great way to measure it. So you're looking at hydrogen H2O. These thermalized neutrons are slowed down by water. The rate of return is proportional to the soil moisture, and it's all done in this internally software gauge. It's tricky. These are radioactive sources. It's shielded, so you have to have some protection, but these are very accurate, and all the way from 0 to minus 1,500 kilopascals of potential. Very nice. And is this destructive or is this non-destructive? So I have a tube in the soil. I put a tube. I lower this device in, and I measure it. I raise it up and measure it. So this is non-destructive. We go back to that same point and measure and measure and measure. So this little thing here, this is about half a foot long. This is put down into an irrigation tube that's used and plumbed into the soil. Go back to that same place and get a very accurate measure of soil moisture. And it's expensive, but it's very, very accurate. Another way to do it is time domain reflectometry, TDR. And this is good and accurate over a wide range, 0 to minus 10,000 kilopascals. And the idea is that this depends, the return of a wave is dependent on the dielectric constant. So the soil dielectric constant is directly related to the moisture content. It's also affected by salt, but can be calibrated against that. But this TDR, this is non-destructive. You put this sensor in, you read out the result based on the rate of return from this wave, and it's a really slick way to do it. Systems like this can, for permanent, you leave these in the ground, pay about $5,000 or $10,000 for a system. But then the only cost is these wave guides, and those are fairly cheap. So once you buy the system, very, very cost effective, non-destructive, but it's a very expensive thing to buy in the first place. And of course, they can be used over and over again, and they're perfect. Well, they're not perfect, they're expensive. Another way is capacitance. So capacitance is a measure of difference in voltage and resistance across a couple of I lost for words, across a capacitor. And this is directly proportional to soil water, fairly accurate, 0 to minus 1,500 kilopascals, and these can be automated. This is a little less expensive than the TDR and a lot less expensive than the Neutron probes. Resistance blocks. These are cheap, but they're not so accurate. Right? So they range from minus 90 to minus 15 kilopascals. So essentially what you have here is you have gypsum, and then you have wires going into them to measure a difference in voltage. Now the difference in voltage across these positive and negative, this is proportional to the moisture, and they get a nice little readout. These are really cheap. These gypsum blocks are very cheap, but they dissolve over time, and they're not so accurate. So if you're doing levels of work that require high accuracy for research, you wouldn't use one of these, but they're probably all right for irrigation. And they're calibrated. So the manufacturer sends you a calibration curve, but if you have specific soil, and you'll find out that if you have, here's soil A and soil B, that a test against this, it was not very agreeable, or it was not as very accurate relative to the calibration. So part of the message is, if you have these, it may be useful to do your own calibration. But that adds time, and so it just will improve the accuracy. But over time, these things dissolve. Gypsum dissolves over time. So it's a non-destructive, relatively inaccurate, but very cheap way to do it. Tensiometer. These are for very low potentials, and these don't even go down to, once you get nowhere near wilting point. So a little bit past field capacity, so they tell you when the soil is moist. But what happens, a tensiometer uses a column of water. So in this picture, I'm showing you this is essentially a porcelain tube, and that's put on the edge of this tube, and there's a gauge that measures the tension and the pressure, tension or negative pressure. So water equilibrates with this, and then will exert a tension on this gauge, and it'll read up to minus 85 kilopascals. What happens is, when it gets any drier, this column will be broken with bubbles, and it's no longer useful. So this is useful for moist soils and maybe at the irrigation level, but not useful for anything beyond that. Thermocouple psychrometer. This is pretty interesting. This is used in dry soils from 50 to minus 10,000 kilopascals, and this actually evaporates water and then measures the difference in humidity and temperature, and this is correlated to the moisture. So this is used it's in kind of desert soils, very dry conditions, but it's also destructive. This is done in the lab, right? You don't do this in the field, the thermocouple psychrometer. And small differences in a dry soil is very useful. So again, used on the drier side of things. A pressure membrane. So last week we looked, or last lecture, not even last week, we looked at trying to develop the soil moisture characteristic, and the pressure membrane is actually used to apply the pressures to get to the higher ends, the lower potentials of that curve, around 1,500 kilopascals. So here's what it looks like. So essentially it looks like a big pressure cooker, and this is a permeable porcelain membrane, and you put a soil sample on here and seal it in, and then you apply a pressure. And so you can apply 15 atmospheres of pressure, usually compressed air, compressed nitrogen, and the moisture in the soil equilibrates with this temperature. And so at 1,500 kilopascals at wilting point, for example, you apply that pressure that forces an equilibrium, the water goes out, and so the moisture left in that soil is held at 15 bars, minus 15 bars of potential, or 1,500 kilopascals. And so then you measure the moisture, and then now you have the moisture content of the soil at minus 15 bars. And what is that? That's wilting point. So this is the way to develop that soil moisture characteristic to getting those very low potentials and lower than that. And it's all due with compressed air or compressed nitrogen, a pressure applied to the sample to equilibrate the water held in there at whatever soil potential we're trying to make the curve for. Okay. Here's a picture of the compressor. This is actually in our old lab. You can see this little air compressor hooked up. All that pressure goes and pushes the air into there. 15 bars pressure equilibrates with minus 15 bars of potential. And then we have another point on the soil moisture characteristic. How cool is that? Okay. Here are some practical implications for sensors. You can put them in the field and hook them up and send the electronic information to a data logger. And now in the field, you can have these non-destructive, and you can actually track in real time the impacts for water and irrigation. So when you have a very expensive crop and you're irrigating down to a very fine level and water is expensive, this kind of operation can be very useful. But you're talking a significant investment, $5,000 to $30,000 for the whole system of the sensors and the software. But some of the larger growers utilize this technology because irrigation in some of the western states is very expensive, and every little drop is accounted for, so you don't want to do any waste. And this is one of the systems, one of many systems, this variable rate irrigation, that utilizes that technology to essentially minimize irrigation losses and maximize profits. Well, that covers pretty much everything about soil water. And so I've got borrow some from Dr. Seuss. The storm starts when the drops start dropping. When the drops stop dropping, the storm starts stopping. And that leads us to soil aeration. Perhaps this is a good place to end, gets you out a few minutes early. Hope that you've had a great week. I will be back late tonight. It's Wednesday by the time you see this. And I'm actually attending the Soil Health Institute meeting. I wasn't really at the stadium, although it would have been nice. So I'll be back Thursday morning. Have a great weekend. Lab this week, hope is going well. The soil water calculations. And I will see you face-to-face Monday morning, or you can drop by Thursday morning after I get back and chat about whatever. Have a great week. Briggs out.